And share my screen, admit people, and there we go. So last time we finished up talking about your quiz that you'll have on Wednesday this week with the locks and blocking and deadlocks and all of that fun stuff. So that'll be Wednesday. We'll have that quiz. And again, you'll be able to use your laptop during the quiz, or if you would like, you can open up one of these computers and use that. You can do anything on the computer except contact each other and open up Postgres itself. So the expectation is that you would be referring to the Postgres documentation in order to solve those problems. And then tomorrow, your first Twitter Postgres assignment is due, where you're inserting stuff into the database. And so now we're in the topic 9 folder. We're going to be talking about this thing, Mvcc, multi-version concurrency control. There will be a homework that I'll post here. The homework is, again, we're going to be, so the first assignment on Twitter Postgres, you're just getting sort of the basics of the insertion into Python, or with Python, or with that copy command into the database, all happening sequentially. So the locks and blocks and deadlocks don't matter because it's all sequentially. But this next homework is going to be doing it all in parallel. And so the starter code is basically it's not exactly the solution to the previous problem, but it's basically that. And you'll have to modify it to make it all happen in parallel. And you'll see that as you're doing that, it'll cause all these locking and blocking and deadlocks to happen. So at the start, your parallel code will be slower than your non-parallel code, but then you'll fix it, so the parallel code will be faster. Today, we're talking about this Mvcc thing about how the database is physically storing information in the database here. And there's this questions.pdf file. We're not gonna be going over exactly this questions.pdf, but this is the sort of thing that you'll want to be able to answer after we're going over the material for this week. These questions that are in this PDF file, and there'll be a couple of subsequent PDF files, will be their sort of sample questions for what to expect on the final exam. And so we'll be going over all this information starting today. Any questions about anything administrative, what to expect, timelines, deadlines, anything like that? We're all good? Okay. Then back over here to our notes. And so again, there's this textbook that we'll be going over today. And there's 5 chapters that you're expected to be familiar with for this textbook. And the questions that will be on the final exam, that'll be an open notes final exam, take-home exam. But the questions can come from any of the material in these 5 chapters. And in class, we're going to be going over the high-level ideas in this textbook, basically focusing on the figures and how to read through this textbook, how to find the appropriate information. About half of the questions that will be on the final exam are things that we'll directly talk about in class, and the other half will be things that you'll have to just navigate the textbook and figure it out for yourself. But hopefully, based on the things that we talk about in class, it'll make sense how to navigate the textbook. Any questions about anything before we get started? Okay. The material this week is I don't know, maybe a little bit hard to be like motivated with, like, why do we care about this material? Ultimately, we're going to be, we need this material in order to fully understand like how to make our SQL queries fast. It's not going to be obvious though at the very beginning why that's the case. So it is maybe a little bit dry or a little bit boring at the beginning of this section, but then starting next week, we'll be able to, in earnest, really talk about making our SQL queries fast and all the different algorithms under the hood that are taking a part in that, and actually writing the SQL code. So this is background information for that. This textbook again, so this first link that I'm giving you right here, that's what we're looking at. This is just this starting set of chapters. You're responsible again for 1, 2, and then 5, 6, and 7. The material in the other sections out here are really about pure CS stuff, data integrity issues, and so important and interesting, but not the focus of this class. In this first chapter 1 here, it's talking about some of the like big picture ideas and terms for Postgres databases. And one of the first things that's confusing about Postgres is just the name nomenclature they use for things. So this idea of a database cluster, oftentimes when we think of clusters, we think of like distributed computing. In Postgres, the word cluster doesn't imply distributed including. It just means like it's an individual Postgres instance, for example, that's been run using Docker. And the databases down here, these are not different Docker containers, but databases inside of the original Docker container. So this whole thing is one Docker container. It's the right way to think about it. In the past, before Docker existed, people often, like if you were building a business to business sort of app, you would have maybe one different database inside of your database cluster per customer and store them all on the same machine. These days, the standard practice is just to have a single database inside your database cluster and have a separate database cluster for each one of your clients that you're working with. So this is sort of like a historical thing that that'll come up in the documentation, but it's not something that people do anymore. There's always just exactly one database per database cluster in modern databases. This green box over here has all the different types of relations that can exist. We've talked a lot about tables. We're going to be getting to these indexes, which is how to make the tables fast here. Inside of this first chapter, there's a lot of these like example SQL commands or example shell commands they're going to have down here. Those are good things to try to make, or good sources of questions for the final exam from this chapter, but we're not going to go over those things in detail. This image right here is just talking about the particular directory structure inside of Postgres, how it's physically storing all of the information on the hard drive. Again, interesting for purposes if you're trying to split the database up onto multiple hard drives, but not super important for our purposes. So we're basically skipping over all that information. And the first really important thing is this picture down here. We're going to spend a fair amount of time on this picture. This is the thing to 100% that you have to understand this, both for the final exam to get a good grade on it, and for understanding how these indexes are going to work for speeding up our Postgres database. So what this is saying is that every table we have in Postgres is going to be stored in an individual file, and this is the format of that file on the hard drive. It's divided up into pages. Each page is 8 kilobytes or 8192 bytes, and then the format of those pages follows this picture over here on the right. I'm going to switch over to a blank screen over here, and I'm going to draw out the important parts of here, referencing back and forth with that picture as we do so. So here, there we go. So we have an individual page. Again, it's 8 kilobytes in size. And at the top of this page, there's this header section. And this header is going to be the same size for every page. So we don't actually have like 8 kilobytes of information that we can work with here. In the I don't know, somewhere in here probably tells us exactly how many bytes this takes up, but each one of these blue boxes here is basically just a number, so it's not a whole lot of information. It's just like 24 bytes, I believe, something very small in the header. And we're going to walk through the steps of what happens when we do an insert command. So here we have, this would be an empty header right here, or an empty page with the header information up here, always again fixed size, and then this is our free space in the page down here. The tuples that we insert, so a tuple is just another word for a row. Whenever we run the insert command, we'll add a new tuple into this page, and we always add tuples from the back of the page, from the bottom of the page to the top. The way these pictures are represented, so we'll call this tuple 1. The memory here sort of divided up into rows, lots of rows here, and the sort of logical structure is that after you go off the end of this top row, so like if this is position 10 right here, this spot right here, position 10, then position 11 would be right here. And then if this is position 20 right here, then 21 right here. And so it's traditional to draw as like a square like this, but it's really inside of like the hard drive or wherever it's being stored. It's just a sequential sequence of bits. And so the actual information, whatever you call your insert, puts the information at the end of this block down here. There's going to be your header and then the data. So we've talked about the format that goes inside of this tuple down here. And in this picture up here, though, where to go? This picture here, they're not considering, they don't care about like the details of inside the tuple. We just care that there's the tuple itself down here. And then every time we insert the tuple up here there's going to be a pointer added. So the pointer is just a individual number, and this number, so I'll make it consistent. They just use the number. They just have the number 1 here, so this refers to the tuple 1. This tells us where in this page this tuple actually starts off. So if this is a small tuple, this might be like byte 8000 or 12 as an example right here. And then if we add another tuple, well, I'll use green for the second tuple, would come right here. This is part of tuple 2 right here. This is also part of tuple 2. And we add another number right here to, this is just going to point to the starting byte of this second tuple right here. And we've seen before that the tuples, they can vary in size even in the same table. So we don't know exactly how big each of these tuples are, just knowing the table, because it might have null values inside of it. So in order to know where these tuples actually exist in the page, we have to have these pointers up here. This space between the tuples down here and these pointers up here, this is called the free space, or the hole. This whole object down here, often called the heap, this part right here, the entire thing, this entire thing is often called a heap page. because it is a page used to store these tuple heaps down here. Those of you who have programmed in C, C++ before, those have the heap internal to the language. This heap down here is designed after the C heap. Those of you who have not done those languages before, but have like seen the heap data structure, this is not at all related to the heap data structure. The heap data structure designed to get you fast access to the minimum or maximum elements of a container, and that's not what's going on here. So there is a limit in practice to how many tuples can fit inside an individual page. And eventually, after we've added enough tuples here and no more tuples can fit in this page, a new page is created, added to the hard drive. And so this table file over here, it's divided up into this sequence of pages, and each page has this same exact format. Any questions so far? Yes. So I want us to take a look at problem 13 here. So this is again from that questions.pdf file, problem 13. No page can have more than 100 tuples in it. Just so that we can get a sense of what types of questions you'll need to be able to ask and answer, and how to do that. And maybe actually before we do problem 13, let's compare it to problem 12. So problem 12 is just a straightforward definition thing here. If we did a search for OID inside of this chapter, we would see that OID does in fact stand for object ID, and every table is assigned a unique object ID. So there's a handful of things that you'll we didn't cover this term explicitly, but you'd be able to look through the chapter and figure that out, or just appropriate Google searches to figure out this information and figure out whether it's true or false. Number 13 down here, there is no like sentence anywhere in this textbook that tells us exactly what the answer to this is. As far as I know, there's no, like you can't just Google this and it will tell you. I have no idea if ChatGPT will give you the right or incorrect answer to this. But the right way to figure this out is using our knowledge of tuples and pages. Is it possible for us to construct a certain type of tuple where we can fit 100 of those tuples into a page? The answer is that yes, it will be possible. And so let's figure out how. So we've talked before that the minimum size of a tuple is going to be how many bytes? That's right, 24 bytes. That's our header information for whatever, no matter what our kind of table we have, is always the 23 bytes plus the null bitmap if it's applicable. And so we'll round up to 24 bytes. And then we never have store null values. So if we're just inserting nothing but nulls into our table, then we'll get 24 bytes. There's other ways that we could get this minimum tuple size as well. But an example of one way to get this minimum tuple size, I'll write it out. One way to get this size is just inserting a row of all nulls. And then the question was asking, can we fit 100 of these tuples in a page? And so 24 times 100 is 2400. That's significantly less than the 8196 bytes of a page. And we still have to account for that page header size. But if we header data is 24 bytes long, so definitely fit because the header data for the page is only 24 bytes. So we're totally good there. If so, the answer to this question 13 here would be false, because it is possible to have a page that has more than 100 tuples in it. If we have only 100 tuples, we still have plenty of space in that free space map. If this was changed from 100 to 1,000, however, then we would run out of space. We would have, so if the question was 1,000 tuples instead of 100, then the total bytes needed would be 24,000, and that's greater than the 8196. So answer is false. Well, the answer is that we can't have, they don't fit. And so the main purpose of why I wanted to highlight this is so that you have a sense of the types of questions that could be asked on the final exam and the types of things that you'll have to work through. Some questions will be just straightforward, take it directly out of the text, but the more interesting and more common questions will be you'll have to somehow apply lots of various bits of knowledge together in order to come up with the right answer about whether it's true or false. Any questions about? Yes.
I just want to clarify one question. Is it supposed to be 8196?
Probably 9. I don't know. Forgetting my powers of 2. 8192. That is 2 raised to the 13th, 14th, 13th. Every page is guaranteed to be exactly 8192 bytes, and it'll just have, you don't have to use all of those bytes. It's perfectly possible to have an empty page that has no tuples in it, but it'll still take up 8 kilobytes of space. The reason why these pages are 8 kilobytes is because in old hard drives, it turned out that you could only save data in chunks of exactly 8192. Modern hard drives, you can vary this size, but for technical reasons, Postgres just sticks around with this, and it still works pretty well. Any questions? Okay. We're going to be seeing some examples of pages in different contexts as well, but pages will always have the same exact format, always be the same size, always have some header information and then some tuples inside of them. The heap pages or heap tuples are what are being directly inserted into tables. So anytime you see like tables, that's synonymous with a heap page, but all these other types of objects will have their own types of pages. But heap and table, those two words go together. The tuples, we saw before that one of the advantages of Postgres is that it supports very, very large column sizes, and it automatically compresses things. So if you had a tuple that, for example, had a text field inside of it that contained like books of documents, that book would not fit inside of this tuple or inside of this page. And so the toasting procedure is how the tuple has a link to that information stored elsewhere on the hard drive. The tuple itself has to fit inside of 8 kilobytes. Anything that's larger than that will get offloaded into a separate representation, but we're not going to talk about those representations. The important thing for us is going to be how each of these pages are stored and how the tuples are stored. The next picture down here is going to get us into the why we care about this a little bit. And these two images on the left and right show the two basic ideas of algorithms that Postgres has available to it when it's trying to access data. So if we're trying to do a select something from our table, so in this case, what they have written here is select star from the table. So select everything from the table. If you're trying to select everything from the table, the only option you have is to traverse all of the pages and then individually go into each one of these tuples and return each one of these tuples to pSQL or wherever you're calling from. We call this a sequential scan because you're scanning all of these tables in sequence. And so this is going to be a linear time operation O of n. These index data structures, they're going to contain special information inside of them, which will tell us exactly which page to jump to, and then inside of the page, which tuple to jump to. So we will be able to, inside of these indexes, store exactly where in these this data structure down here we're going to jump to instantly. It'll take us, we'll see logarithmic time for most indexes to travel through the index. But once we get the particular, it's called the tuple ID, the TID tells you which page and which tuple you're inside of. Once you get the tuple ID, it'll take you constant time to access any particular tuple. So the purpose of the index is going to be to give us the tuple ID that corresponds to something that answers our query. And then once we have these TIDs, we can have all our operations take constant time to do the lookup. So we'll take a look at these indexes starting next week, how they work. The rest of this week, we're going to see all the weird edge cases that happen with this data structure right here that's going to add additional complications to what we're talking about. Any questions so far? Okay, I will try to keep this as interesting as possible for us. So this is all in this first chapter here. And where we go? On to the chapter 2, the process and memory architecture. So here's a basic diagram of all of the processes that are running inside of the Postgres server. And everything in this square box right here, you should be thinking about as being inside of the Docker container. And every one of these blue boxes here, these are a process in the operating system. So it's something that would get listed by the PS command. So there's not just like one Postgres program that's running. There's actually going to be dozens, potentially hundreds of Postgres, different Postgres programs running. The stuff out here, these clients, these are not necessarily inside of the same Docker container, but inside a different Docker container or like your Python program. And they're connecting over the network somehow to Postgres itself. A couple of, well, let's see, most of these processes are more interesting from a pure CS data integrity perspective, but a couple of these will be interesting to us from our performance perspective. And so we'll talk about those one at a time as needed. The main interesting thing here from chapter 2, though, is this figure 2.2 about how the memory is handled inside of different processes. These temporary buffers, work memory, and maintenance work memory, the important thing here is that these are going to happen on, or these are values that apply to an individual backend process at a time. And we'll see that as we are doing various types of algorithms to access our database, we're going to be able to tune these different parameters. And so these parameters here, these three parameters, they apply per backend process, so per query. There's one backend process for every select query that you run, or every transaction that you're inside of. Every session that you currently have has a single backend process. And so these parameters are per query, and then these parameters down here are going to be shared by everybody. So we're going to get in a little bit to like tuning the size, how much memory you're allocating towards different processes. And this will be your reference to figure out which things, whether it's an individual part of the backend process or the shared memory. The most interesting of these chapters, or the hardest of these chapters, is chapter 5, this concurrency control. And this is again related to the locks and blocking and how all of that is implemented. I'm going to scroll down to here. Our heap tuple header data. So again, we talked about before that there's this 23 bytes inside this heap tuple right here. The null bitmap may or may not exist. And all this information, even though it's not actually inside of the listed as a column in the table, these are things that we can access inside of Postgres to get access to like this xmin or xmax variable in the header data. And each one of these values, the X here, what you should think about with the X is transaction. Every time you see a transaction, an X, that's a keyword for transaction. And so we talked a little bit about how the insertions happen, but we're going to go into a little bit more detail now with this xmin and xmax and how it relates to the individual transactions themselves. So here, under our tuple 1 and tuple 2, again, the ordering is sort of reverse, starting with the lowest numbers to the right and the larger numbers to the left. They get inserted from right to left. We know that, or these xmin and xmax, the transactions that these tuples are visible, there's a sort of complicated formula that uses all 4 of these pieces of information right here. I'm going to scroll down to the section of code they have that tells whether a transaction or whether a particular tuple is visible or not. This is this visibility check rules. And the actual formulas for determining whether a transaction can see a tuple or not are complicated. So there's this piece of pseudocode, this piece of pseudocode, this one, and then these other additional rules down here. I'm never going to ask you on the final. I'm not going to ask you to like work through, is this particular tuple visible or not. I just want you to just have a sense that the rules here are very complicated to determine whether a tuple is visible or invisible to a particular process. This xmin and xmax, though, a very important feature about the xmin and xmax is that they are only 32-bit numbers. So all transaction numbers in Postgres are 32-bit. And so that implies that the largest, I'll just use my X, the largest transaction number is 2 to the 32, about 4 billion. And so by default, if you don't do anything special, then you could only have 4 billion transactions ever in your database. And that seems like a lot of transactions. But if you consider like a web page, every time somebody's connecting to the web page, you have a separate transaction. Then a company, say like the size of Instagram, is going to be going through all 4 billion of these transactions within just a couple hours. Goes through transactions really quickly. Every few hours. And in general, even companies that aren't Instagram that have so many transactions all the time, there's everybody runs into this problem of running out of transactions. So the way that Postgres handles this problem is what's called transaction wraparound, and it treats the transactions as there's a maximum transaction number that you'll ever have. So in this case, in their example right here, this figure 5.1, transaction 100 here is the current transaction that we're at. Anything less than 100 is a visible transaction, one that we can see because it's in the past. And anything that's greater than 100 is something that's invisible, something that we can't see because it's in the future. But at some point, at this number 2 to the 31 plus 100, so halfway through the 2 billion mark, there becomes a transaction that we're able to see again. And so half of the space is always going to be invisible and half of the space always visible. So it's wrapping around our 32-bit number here. The Postgres always stores what is the last visible transaction that you have. And it won't let you create new transactions if that last visible transaction is still active. So by active here, I mean that you're still somehow connected. Like if you have a Python program that has run a begin command, won't let you make new transactions if that transaction is active. And so active here means that you have a begin, with no commit or abort. And so if you have a long running transaction, which can happen if you're inserting a lot of data at once, then at most you can have 2 billion concurrent transactions with it. You have to end this transaction before that you're allowed to have that 2 billionth and one first transaction. There are some subtleties involved in keeping track of all of this information about what transactions are visible and not visible that we're not going to go into, but there is a process called auto vacuum. Auto vacuum that handles these transaction issues, that handles the background information for the transactions. This auto vacuum program is something that's unique to Postgres, doesn't exist for other so it's unique for Postgres and doesn't exist for things like MySQL or Mvcc. But this is the first main issue that auto vacuum deals with. It makes sure that you are have a sufficient number of transactions available. So the first purpose ensures you have sufficient transactions available. The second purpose, which is will be easier to illustrate and get an intuitive sense for, is that it will free up your hard drive space after you run delete commands. Free up space after update and delete commands. Any questions so far? Yes. Yes. Dryish material. I apologize for that. Feel free to ask questions about off the wall things that are just sort of inspired by this, or details about this. Yes.
Is it helpful to have, so all these transactions are active, or they were just like in the past? Just
Sorry, can you ask the question again?
Yeah, I don't really, so just like, for example, before 100, all of those transactions happen. Are they no longer active, or some of them are active, some are not?
These transactions are in the past, meaning they are visible. We can see their effects of what's going on. They are not necessarily active or inactive. They're just visible. So with this X-min and this X-max value, where did it go? Essentially, the short version is that any tuple whose X-min and X-max values, your current transaction is between these two values. You can see that tuple when you do like a select query. And the auto vacuum, if the X-min would be coming below this value up here, auto vacuum will move up the X-min values to a more current number so that more transactions are still able to see it. Yeah, the main important takeaway is that there is a problem related to the fact that there's only 32-bit numbers, and auto vacuum fixes that problem. I don't know if that answers the question, sort of. Question? Yeah, so we haven't talked about the second purpose of the auto vacuum yet. The second purpose of the auto vacuum is how it frees up space after update and delete commands. So let's take a look at exactly what's going to happen in an update and delete command. With an insert command, we've seen intuitive idea of what's happening, that we're filling up this free space map with more values as we insert tuples. With a delete command, though, we never actually delete information from our hard drives. This is the key thing about the way that Postgres works with this multi-version concurrency control, is you never delete information when running an update or delete command. So instead, when we get to a delete operation, what happens is that the transaction max value, the maximum visible transaction, gets updated to be your current transaction ID. So if our current transaction ID is 111, when we run this begin delete from table commit, then the X max ID is just updated on the hard drive to have the max number be 111. So that way, if there's another transaction, whatever the next transaction is, 112, 112, its maximum value will be bigger than 111 here, so it won't be visible. So the only thing that the delete command does is it just updates this X max value right here. It doesn't actually remove anything from the hard drive. So delete only updates the X max, and this is needed to ensure that a previous transaction that's still running ensures a previous transaction in, for example, the read repeatable mode. Would still have access to that tuple if it needs it. If you have an update command, there's no special logic for an update command. Instead, an update is literally implemented as it calls the delete function and then an insert. So the update command is going to change the Tmax value, and it's making that particular tuple not visible to the to certain transactions, and then cause or run an insert command adding another tuple somewhere else in the table. The main important thing to take away from this is that, so there's lots of weird edge cases that we're not going to go over about what happens if you have various transactions going on. But the main important thing to take away, where's the figure that I'm looking for? Here, this figure, it's in the chapter 6. So under chapter 6, vacuum processing, is that some tuples in your page will be visible, meaning there's some transaction that can see that tuple, but you also have some tuples which will not be visible, potentially. If you've been running a lot of deletes or a lot of updates, then eventually that the tuple, the header information that corresponds to that tuple will no longer have transactions that can look at it. All the transactions will be bigger than the Tmax value. And we call those tuples dead tuples because nobody can view that tuple. That tuple is still taking up space on your hard drive. It's still inside of your page headers here, or sorry, inside of your pages. And the delete and update commands never remove dead tuples. The thing that removes the dead tuples is this vacuum process. The vacuum will identify that there's a dead tuple right here and delete that dead tuple, combining tuple 1 and then tuple 3 right next to it. So that's the main, or that's the summary of what the second purpose of the auto vacuum process does, is it frees up space after update and delete commands, because the update and delete commands never actually delete information from the hard drive. They just modify that Tmax value. And then eventually that tuple might not be visible anymore. So the vacuum command is what actually frees up the space, deleting that dead tuple, and then the free space over here is larger. Question?
So will the space for the pointer always be
And then your questions about this too, right here. And then when the vacuum does delete this dead tuple, The two over here no longer has a tuple that it can point to, but that two still has to exist there for complicated internal reasons. And so it is the case that vacuum by itself can never fully recover all of the space. Each one of these individual things is 2 bytes, so it's not too much like lost overhead. Um, but that is something that the vacuum cannot recover.
And can that be used?
If we were to then insert another tuple here, it would add a 4 over here, and it would point to a tuple 4 over here, and this 2 is just not going to be ever reused again. But we can reuse this free space here. Yeah, good questions. This vacuum command is an individual command that you can run all by itself inside of Postgres. You don't, it's just vacuum, then the name of the table, and it'll run this on the table, go through one page at a time. But you don't ever have to manually call the vacuum process. That auto vacuum runs in the background doing these transformations at time intervals that Postgres thinks are good time intervals. If you're doing large inserts or if you're doing, so from a data analysis perspective, what are the main takeaways here? If you're doing a large set of inserts, then it's common to temporarily disable the auto vacuum so that it's not going through and scanning. Temporarily disable the auto vacuum so that it's not going through and scanning your table while you're trying to do all these inserts, and you know that auto vacuum's only helping the updates and deletes, but then you would re-enable it afterwards. If you're doing a large set of update and delete commands, then it would make sense to manually run the vacuum command. And not wait for the auto vacuum to do it. And by doing many updates and deletes, this would be like maybe 1 million updates and deletes, then run a vacuum, then do another 1 million updates and deletes and run a vacuum. One of the, let's see, any questions so far? One of the disadvantages of the vacuum is how, let's say we have this situation right here, that on the left-hand side, we have a set of 3 pages that all have just one tuple inside of them each with many dead tuples. This is a very common thing to have happen when you're running lots of updates and deletes. The vacuum command will not actually free up space on your hard drive, because when we run the vacuum command, it deletes all these dead tuples by moving the live tuples or visible tuples to the end over here, adding more free space inside of each page. But the vacuum command by itself never combines pages together. So the vacuum command, since it never combines pages together, is never combines pages. It's going to be relatively fast, but it's not going to actually free up disk space. Instead, if you actually need to combine these pages together into a single page, then the command is a full vacuum that you would use, full vacuum instead of a regular vacuum. And a full vacuum is a very annoying thing to do as a database administrator because it acquires an exclusive lock on your table. Nothing else can access the table while you're doing a full vacuum. And the reason for that is because it has to rewrite everything that's inside of the table. It creates this new page over here, basically a very empty, totally empty table, copies things over one at a time into this new table file, and then deletes whatever your old page was. So the full vacuum will free up disk space, but it's expensive to run, both computationally, and you can't run anything else while the full vacuum is going on. Question?
So in this case, it does delete the dangling pointers.
And the question before about these, if you're running like this 2 over here, the vacuum process does not delete these pointers to the tuple. The full vacuum will actually delete that and free up space. In practice, on a modern system, disk space is fairly cheap. So the full vacuum basically never used, and just the vacuum is used. The vacuum call itself has a pretty generous lock on it, just a sharing lock. So you can do basically everything that you would want to do while you're vacuuming. There's no there's a slight performance hit while the vacuum is happening because it's accessing the hard drive, doing some computation, but it's not going to block any of your computations the way the full vacuum will. Any questions about that? Yeah, go on.
So like when you call the regular vacuum and end up in a situation like this, if you start inserting new tuples, you still insert in those empty spaces, or does it have to be like you have to make it a page?
So yes, this is a great question. The question is, well, if we're in the middle of a vacuum process and we try to insert something, where will the insert happen at? And this brings us to something called the visibility map and the free space map. Both of these are going to be important concepts for how the indexes work. So they're important for understanding for vacuum, but they're also going to be important for the indexes and looking up information quickly. In the visibility map over here, the visibility map is just a sequence of zeros and ones, where a 0 in the corresponding visibility map entry indicates there is a dead tuple somewhere inside the page, and a 1 indicates that there are no dead tuples, so everything is visible. When the vacuum is actually processing the table, it goes through the visibility map and just looks at each page one at a time for each one of these zeros, and it skips over the page if it has a 1. So if a table is regularly vacuumed, then the visibility map will have almost all 1s everywhere, and so the vacuum process will be very fast. It won't even have to access any of these pages at all. When the vacuum is doing its actual access to the page over here, there's something called a page level lock instead of a table lock or a row lock. The page level lock will cause that page, nobody can read or write to it while vacuum is working. And then once vacuum is done, it'll release that lock, and then the insert command can add to it. So the vacuum process is only locking one of these individual pages at a time, and all the other pages are totally visible to it. The free space map, free, so the VM stands for visibility map. VM is the visibility map. FSM is the free space map. And this stores how much free space there actually is inside of each tuple, or sorry, inside of each page, or stores the size of the free space. So I don't think there's an actual like figure illustrating the free space map, but it's just a list of integers, one for each page that says how many bytes are available. So it'll look something like 70 for, these are some relatively full pages, then a relatively unfull page and another full page, and then one more very free page. This is what the free space map looks like. And when you're actually performing an insert or a delete, or sorry, just an insert operation, it'll go through the free space map, look to see which one of these pages has a space available to it, and then it will insert into that page if that page is not locked currently by a vacuum process. Did that answer your question? Can I lose some? We're in there.
I mean, like, if all of these are not locked, it would just insert into like, the first one.
Yeah, well, the question is, would it insert into the first one? Probably. Most technically correct is we'd say it would insert into an arbitrary one. There's no like guarantee about which one. If we had a tuple that was going to be like 1,000 byte tuple, could be inserted either here or here, and internal heuristics would determine which one's the better one to do. But so the vacuum process, where the vacuum command will update the visibility map, update the free space map, and update the individual blocks. Any questions, other questions so far? The last chapter over here, there's something called a heap only tuple, which is related to this thing called an index only scan. Turns out that there is a special situation in the update command where it won't do an insert and delete and will actually update things directly in the page itself. That's called a heap only tuple. We'll talk about that when we talk about index only scans. So this is a chapter that you will be responsible for. We're not quite there yet, though. Next time we've covered all the background that we'll need to talk about these indexes and actually creating indexes. So that's what we'll get to next time, and that's everything for this Mvcc chapter or section. Any questions about any of that? Okay. I realize it was a maybe more boring class, but all that background information will be needed for talking about these indexes and making sure they're actually fast. So that's what we'll do next time. If anybody has, yes, question.
For the visibility map, is that just saying whether or not we can see that thing?
One way of thinking about it, question is for the visibility map, right here, do the zeros and ones mean that they have to be vacuumed? And that's one way of thinking about it, that a zero here indicates that page should be vacuumed, which is equivalent to saying that it has the dead tuple inside of it. Yeah. So this is the most important thing that the vacuum is doing. It's updating the visibility map here, knowing what's zeros and ones, getting rid of these dead tuples. It's also doing something weird behind the scenes and for transactions. But this idea of the visibility map and removing these dead tuples will be the most important thing for our indexes and speeding those up. If anybody else has other questions about this stuff or your homework assignment, I'll stick around after class and get those answered, but otherwise we'll end early today. So see you all on Wednesday.